Welcome to this video in which we are going to discuss the basics of mesh-based computational fluid dynamics. And the whole concept is based on the idea that the fluid can be treated as a continuum. And based on that, the fluidic domain is divided into discrete cells which form the so-called mesh. And this is illustrated on the right. Here you see a cyclist, and the aim of the study is to calculate the flow field around this cyclist. So the area around the cyclist is the fluidic domain. And as you can see here, the whole fluidic domain is divided into small cells. And as can be seen, for example, in this image, there are different types of grids. So you can have a structured grid where you have cells that look regular, or you can have, for example, here or here, an unstructured grid where the cells are more or less deformed. And as you can see in this image, those meshes can be quite complex. And the generation of a high quality mesh is quite important because with this approach, the governing equations are solved for each of those small elements. And if those small elements are set up in a bad way, your solution won't be valid. The solving itself is then done by converting the governing equations, which are usually partial differential equations, into an algebraic system. And this is done with the help of this generated mesh. And we're going to discuss this on an example in the actual lecture. Once you have performed your calculation, you end up with the data, which can then be visualized in all of those cells, and you end up with an image or visualization of your results like this. And there exist various applications for this type of approach. This is probably the most common approach when we talk about modeling and simulation in the area of fluid dynamics. So mesh-based computational fluid dynamics are used in basically any engineering problem that deals with fluid flow. It can be problems dealing with aerodynamics or with chemical reactions or heat transfer problems. So all those areas are covered by this approach. And I would like to finish with some remarks on this technique. As we just discussed, it provides spatial and temporal resolution of field variables. For example, the velocity, the pressure, the temperature, concentration, and so on. But for each of those variables, of course, you need to include the governing equations into your framework. And the amount of or the number of equations you include in your model significantly determines the computational effort. So those simulations are quite resource demanding, at least if you want correct results and have a large fluidic domain you want to simulate. And you should take away that this whole approach relies on the discretization of the governing equations. Again, I would like to refer you to the actual lecture where we're going to do this for a very simple example. Basically, this discretization can be done using mesh, as we just discussed, or it can be done with the mesh-free method, which we discussed in the previous video. And this discretization, which is the transfer from the partial differential equations into an algebraic system, can be done by various techniques. The most common ones are finite volumes or finite elements. And the last thing I want you to remember is that setting up a working CFD simulation, and this includes the generation of a high quality mesh, requires extensive verification and validation.